So we'll start with something simple. Let's take a ring. If we have a ring and if you pour some charge over the circumference, so no matter what is the distribution, the potential at the center will depend on total charge, not on the distribution, right? So if the total charge given to the ring is Q, whether it is uniform or non-uniform, the potential at the center will be same. The reason is every charge is at equal distance from the center, right? Am I audible to you?
Sir, yes, sir, sir, am I audible to you?
Now you're audible, yeah. So if you choose any elementary part of ring which contains charge dq, so the distance of this point charge from the center will be r. So you can write as potential k dq by r. But because r is constant for every charge, so the integration you can directly write as dq integration. And if you add all charge on the ring, it will be equal to the total charge, right?
Yes, sir.
So what we can say that here the distribution doesn't matter, isn't it?
Yes, sir.
So charge distribution doesn't matter. All right. So what I'll do is next is again we have a ring, but now I put a charge uniformly. So now this is the uniform charge distribution, and we are going to do something very challenging. So finding the potential at the center is very easy. But now I would like to find potential at a distance, although very close to the center, but slightly ahead. And the distance is r, and the radius is capital R. And r I am taking as very small compared to r. So now we would like to find the potential at point P, which is in the vicinity of center, but not exactly at the center. Okay. So this is going to be a challenging problem, and let's see how we can solve. So this is like a, you can think of Olympiad level problem, not just JEE advanced. It is more challenging than JEE advanced. So, so what we do is from the center, actual center, we move theta and we move d theta. And because it's a very small angle, d theta, as you can understand, this is theta. And the point P is slightly ahead. So I'm just doing it slightly here for the sake of doing. So we need to know what is the distance here, right?
Yes, sir.
So we may call this as R dash. Okay. And this charge is here, which is dq. So now we can write the potential elementary value. So we can add dVp is k dq by R dash, right?
Yes, sir.
So we can convert R dash in terms of capital R and small r and theta, because we know the cosine law.
Yes, sir.
So R dash is basically under root of r square plus small r square plus 2 r cos theta. Can we write like this?
Yes, sir.
You're okay with this, or shall I explain?
Sir, we have,
Mine.
oh, got it, sir.
So r dash will be this much. So because r is very small, so we have to think about something called approximation. So we can write dvp equals to k dq by r dash, where r dash square is r square plus r square minus 2 r capital R into cos theta.
We have to cancel out the small r square for approximation.
Yeah. So if I take r square common, it becomes r by r whole square, and this becomes 2r by r, right?
Yes, sir.
Cos theta. Yeah. So what you said is correct. We can ignore this part. So this is square, but we'll keep the term which is not square, and the r dash turns out to be r into 1 minus 2r by capital R cos theta power 1 by 2. Okay.
Okay, sir.
So now the next step is called binomial approximation. So dvp we can write as k, and dq, how to write dq? So we can write dq as lambda r d theta,
Yes, sir.
and r dash we can write as r1 minus 2r by r cos theta 1 by 2, right?
Yes, sir.
R cancels out, so the dvp that is k lambda, and because it's again the capital R is bigger than small r, so we can again further use the binomial approximation, like minus half, and we use the binomial approximation by multiplying the power, which will make it to 1 plus r by r cos theta d theta. Okay. So now it is now integrable, because what we are doing is we are trying to make it integrable, and this is the process by which we can do it. So the potential at point P will be integration of dVp, which is k lambda, which is constant. I can take it out, and then I have something very simple. From then theta I have to take from 0 to 2 pi, right? The voice is coming very feeble. I mean, is the mic available?
Sir, I mean, I'm using the same device only, sir.
Yeah. No, it's fine. No, it's fine.
Okay.
So the first term is very easy, just theta, so it will be k lambda 2 pi, and the second term will be k lambda r by capital R integration of cos theta. Uh, shall I keep the second term also? Otherwise, this term will be 0, no? Because the cos theta d theta will give me 0 answer, right?
Yes, sir.
0 to 2. So I think the second term should also be taken into consideration. Otherwise, we will left with nothing. Just now.
So we're not gonna take that term as zero sum.
Yeah. So we should not take that term as 0. Rather, we can just continue the r dash as r 1 plus r by r whole square minus 2 r by r cos theta power 1 by 2. So we can proceed in a similar fashion. See, we have to always keep things which should not make thing zero, otherwise it is of no use. So k lambda r d theta upon r dash, which is r 1 plus r by r whole square minus and we can treat this entire term as single term. So it will have the similar relation. So this will be like k lambda and 1 minus 1 by 2 r by r whole square and plus r by r cos theta d theta. Okay, using the binomial approximation. Okay,
Yes.
so the VP will be k lambda into integration of 1 by 2 r square by r by r whole square plus r by r cos theta d theta from 0 to 2 pi, right? So the VP turns out to be k lambda, and this will be 1 minus. Okay, now you can simply integrate. So k lambda into now we can add 2 pi, the first term. The second term will be 1 by 2 r by r whole square into 2 pi.
Yes.
And the third term will be r by r into integration of cos theta d theta from 0 to 2 pi. This will be 0, right?
Yes.
So VP turns out to be k lambda 2 pi minus pi r by r whole square. Okay.
Yes.
So we got the potential at a point P as a function of r, and this is what I was looking for. So at a very close position of center, the potential turns out to be k lambda into what was that? 2 pi minus. So I can take k lambda pi outside. 2 minus r by r whole square. So the lambda we can write as charge upon 2 pi capital R and
Yes.
so the VP turns out to be q upon 8 pi epsilon naught r into 2 minus r by r. So we will try to verify this. So if r is 0, the answer is exactly k cube by r,
Yes.
which means this is the right equation, because at r equals to 0, we should get the answer. Okay. And we cannot do it for other values of r, because this has been derived with the assumption that r is really small. So we cannot take a big value part and prove that this is true or false. So when we have the potential, we would like to find the electric field as you move along the r. So what is the ER value? So we know the formula minus dV by dr, because now we are interested in finding the electric field nearby the location. So at center, the electric field will be 0, right?
Yes.
So definitely, if there is a uniform ring, if the ring is uniform, the center will have 0 electric field. But if you slightly try to go this way, the point at P, the net field will be towards left
Yes.
because of the symmetricity. Okay, it will be always towards center. So field you will get some value of field, and this we can derive from here easily. That's the whole purpose. So we can write minus q by 8 pi epsilon naught r, and if you differentiate 2, it will become 0, and this will become minus 2r by r square. Okay,
Yes, sir.
the electric field in the vicinity turns out to be how much? Q upon 8 pi epsilon naught r cube into r, 4 pi. Sorry.
So, yes, sir.
So this tells us that the moment you try to move towards the right, you will get a field, and the direction of field will be towards left. Okay,
Okay, sir.
so all right. So the electric field, they will ask you what is the electric field in the vicinity of the center, and this is the answer. And if you look carefully, this we can write as q upon 4 pi r cube. So what I'll do is I'll multiply by 3 and divide by 3. So this is like q by 4 by 3 pi r cube into r by 3. But sorry, up to now. But if it looks like this is the volume charge density, right?
Yes, sir.
So it looks like it's a volume. So formula is like this, and you will be wondering why the formula is coming this way. Okay.
Yes, sir.
So it is like two spheres are almost coinciding, and the gap is r. And because the gap is r, so the field between them will be rho r by 3 epsilon naught.
Yes, sir.
So it is like there is a cavity. So they almost coincide, and the gap is r. So the center is just mismatched with r. And we know that electric field within the cavity is always rho r by like the gap upon 3 epsilon. So this is the formula we use, right?
Yes, sir.
So this is like a kind of the whole idea we can bring to remember the answer, but this is not the answer. Definitely, charge is here surface charge. We don't have the volume charge here, but this is how we are trying to interpret. Understood?
Yes, sir.
So that you can remember the answer easily in future.
Okay, sir.
Understood?
Yes.
So I think there's one more problem. I think should I think this is a problem with the plus and minus sign. So I was wondering. Correct. So I don't know why, but the intuition says that the sign should be positive here. Just a minute. Let me think about it. Okay. So
Can you just come back in a minute?
yeah, yeah. Are you there?
Sir, yes, sir.
Okay. So there is a problem. I'm just trying to figure out the problem. I got the actual answer. This is the actual answer. This one. So this is using Gauss law.
Yes, sir.
So I have drawn a very small cylinder just across the center of radius r and length 2x, x on the right, x on the left, and we know the electric field due to the ring, right?
Yes, sir.
At a distance x.
Above
So
and above or below the plane.
yeah. So above or right or left or like this. So when x tends
Yes,
to
sir.
0, the formula is this much.
Yes, sir.
And therefore the flat surface will have this much flux. E into pi r square
Yes, sir.
on both sides. Okay. And the electric field will be radially inward. It will be entering the cylinder from the side surface, right?
Yes, sir.
And therefore the flux will be ER into 2 pi RH, which is 2x. And it is
Oh,
minus because it is entering into the cylinder, so that's why it's minus sign. Okay.
yes, sir.
So the net flux is 0 because there is no charge enclosed. So in this
Oh,
cylinder, we don't have any charge, right?
yes, sir.
So the field will be 0. Sorry, the charge is 0, so flux will be 0. And if I equate this flux to 0, then the solution will be the radial field because we know the Ex. So I will substitute Ex here, but we don't know Er because we are trying to calculate. The Er turns out to be this value, KQ over 2RQ.
Okay, sir.
But here the things are not satisfying. So I need to look what's the mistake we have done. I think mistake is not there because that's a correct one. Okay, and so if I take this R square common, so that is okay. So K lambda r is equal to R is this much. If I take in the numerator side, it will become minus half, and it will make it like this. That's it. Ah, so the integration from this will be okay. Let me just check. K lambda pi 2 minus r whole square. Lambda is If I differentiate,
So what was the answer for the Gauss theorem method, sir?
it's just 1 by 2 factor. The factor is missing. So it's a KQR by 2R cube, and we are getting here a KQR by. So our answer
Just
is
R cube.
KQR by R cube. So that's factor of 2 is missing, and why it is missing? I'm just trying to figure it out. So, mhm. Is it because of approximation or
So, but the one-year approximation that we used was the binomial approximation.
yeah? So in binomial approximation, we have many terms, but the other term will be high power, right? Okay, let me just check this part. 1 minus. So what we have is R by R. If I take in the numerator, this is the term. So 1 plus x power n will be 1 plus nx plus n into n minus 1 by 2 into x square, and then so on. So if I use this expression, and if I choose this entire thing as x, then it is 1 plus, or you can say 1 minus, the power is negative, minus 1 by 2 r by r whole square minus 2 r by r cos theta. So this is the first term I should write here, and the second term is n into n minus 1 upon 2 into x square.
So, but that's going a bit too complicated.
Yeah, just let me. So if I do it one more step, then
So, but isn't that like a value tending to zero, like second power?
yeah. So this is like 3 by 2 and 1 by 2 is 3 by 8 now,
Yes, sir.
and this will be a square, which is even smaller. So the fourth power will be there, which you can ignore eventually. And then we have 4r square by r square cos square theta, which you can again ignore. Or if you don't ignore, then you can write like this. And then we have the term which is the cube term, right?
Yes, sir.
Okay, so okay, yes. The third term is how much? Third term is 2ab, which is the cube term, right?
Yes, sir.
So this turns out to be how much? Okay, 1 minus anything more than 2 we can ignore as of now. So we have then plus 3 by 8, and any high power than 2, let's ignore it. So we can ignore the first and the last term.
Okay, sir.
So we are left with the
4r squared by r squared cos squared theta.
yeah. And now we can add something. Right? 1 minus r by uh, 1 by 2 r by r whole square plus r by r cos theta, right?
Yes, sir.
And then the last term is like 3 by 2 r square cos square theta, right?
Yes,
And
sir.
if you integrate, then this term will be like a constant. This term will be 0 if you integrate, but this term will give you some answer. How much? The cos
Uh,
square will be having an answer. I think uh,
so we integrate 1 plus cos 2 theta by 2.
it's a pi. The answer is pi.
Okay, sir.
So that term will become pi actually.
Oh,
Yes, because the integration of 1 by 2 into d theta is pi by 2. Sorry, 0 to 2 pi, so it's pi. And the cos 2 theta d theta will give you 0 answer. So the second term will not count. And this will give you the answer from like pi. So, okay, just you can ignore this part. So 1 by 2 r by r whole square. And then we get plus 3 by 2 r by r whole square. Okay, whole into, so this is 2 pi. So I think, okay, it will become 2 times, and this will become pi. So now this we can solve 2 minus r by r whole square plus 3 by 2 r by r whole square, right?
yes, sir. So it will become 2 plus 1 by 2 r by r whole square into pi.
Exactly, exactly. So I was thinking about the same. The answer should be 2 plus actually. Yeah. So we have to go for the greater approximation, which is very complex. So it is eventually 2 plus 1 by 2, right?
Yes, sir.
Into pi. Now this makes sense. So, okay, ignoring this approximation, so we have to make it a more complex approximation, which I will just fulfill here. So this is not a simple approximation. Okay. We have to ignore this entire part, right? And we
Yes,
have to
sir.
take the using higher order approximation. The dvp turns out to be k lambda d theta, and this term we are writing as 1 by plus 3 by 2 like this, right?
Yes, sir.
What we did here. So we got this much. Yeah, this is the answer. This is 1 minus. K lambda theta into 1 okay, minus this one. This term you have to use. Okay, this is the big approximation, and then this turns out to be how much answer? I'm going to write the last answer. K lambda into 2 2 plus r by r whole square. So it is K lambda 5 into 2 plus r square by 2 r square, right?
Yes, sir.
And K lambda pi is how much? K is K. Lambda is q by 2 pi r. Yeah, this makes more sense now. See, again, if I put r equals to 0, I will get the answer k cube r, right? Which is correct answer. And I was expecting plus answer, so yeah, it's a very high degree approximation,
Yes, sir.
and you can totally ignore this calculation. This I'm doing just for the sake of doing. I just wanted to do this for a long time, so I thought of experimenting with you. So now this formula will be apt. Now this formula will give me all the right answer the way I want.
Okay, sir. Sir, but for this question, the recommended method is the Gauss theorem method, sir.
Yeah. This question is actually this is a question of Olympiad level, like international, not national. The last stage, and they'll give you to solve this question. They'll give you almost 2 hours.
Okay, sir.
So now um, the VP turns out to be KQ by 2R into 2 plus R square by 2R square. Now I can find the electric plus minus dVP by dr, and I should get a negative answer because it should be inward. And now this is 0 plus 2R by 2R square, right? The differentiation. So E turns out to how much? KQR upon 2R. This is perfectly coming, right? The way we wanted to get this answer.
Yes, sir.
So this is the electric field in the radial direction, so like along the surface. So in the plane of the ring, the electric field will have the formula K minus KQR by 2R, which can be done easily using the Gauss law. That's correct.
Sir, are you speaking something now?
No, this one understood. This is clear.
Yes, sir.
So this is the field along the plane of the ring, but
Okay, sir.
very close to center. Very close to center. So if you go from center to the point P at a distance r, then the net field will be like this, assuming this ring is uniformly charged, and this electric field will be given by the value is KQR by 2RQ. Yeah. Okay. And this method is easier one, right?
Yes, sir.
So using Gauss law, the net flux will be zero because
Uh,
inside
So,
this cylinder we don't have it. Yes, tell me.
sir, can you just like explain me like how we took the components for the electric
Yeah.
field?
So first of all, to solve this question, we have to go back to the formula of electric field on the axis of a ring.
Uh, that one I got it, sir. Just that the flux. How did
Yeah,
we know like only the EX component will like? All right.
because we're trying to draw a very small cylinder. So cylinder is really small like this. So one surface is just behind the center, and just in front of center. On
Yes, sir.
left, so it's like on the left of the ring and on the right of the ring.
Okay, sir.
And it is so small that this length, I mean, I'm taking the half length of cylinder as x. So half will be also x, the other side. So that is how I have drawn this. It looks bigger, but it is not this much big. Okay.
Okay, sir.
So now from the flat surface, the x component will create the flux.
Yes, sir.
From the lateral surface, the ER, the electric field along the surface, will create the flux. And x is very small, so we can take the surface value almost same everywhere, right? So here
Oh,
the x is as good as zero.
okay, sir. But then in reality, it's just like a layer. But then
Yeah.
since X is very small, we can take it as the entire lateral surface area.
Yes, exactly. So x is so small that it is as good as a almost a layer on both side of center. And the ER we can take almost constant for that layer. Okay.
Okay, sir.
And so we can add the flux like this. So ER into 2 pi Rx, 2 pi RH, H is 2x here. And EX will be EX into pi r square from the flat surface into 2 times because left and right. And the sum will be 0. So this is the answer. Okay.
Okay, sir.
All right. So okay. So this is the method 2, and this is how we can uh, get the answer. Okay.
Okay, sir.
Now Gauss law will give you directly the answer of the electric field. So the potential will be difficult to find, but Gauss using the electric field we can only find the difference of potential. Understood?
Yes, sir.
So so the reverse process of derivation will be like this. So let's say using Gauss law you got the electric field. Okay.
Okay, sir.
I'm just drawing it bigger, but this is this is P, and the field is towards center, right?
Yes, sir.
So we know that relation that the P is at high potential, O is at low potential. So Vp minus Vo is ER into dr integration.
Yes, sir.
Okay. So okay. So we can write as Vp minus Vo is ER is how much? KQR by 2RQ, right?
Yes, sir.
So this turns out to be like this: KQ by 2RQ into. It is 2RQ only. No? Just let me check.
Yes, sir.
Sorry. Yeah. Yes. Yes. So E dot dr we got this answer, which is all right. And now the potential of O we know. So potential at O is K cube by R.
Yes, sir.
So we can take common as if I take common as K cube by R, what we get? 1 plus
1/4 R square plus R square. R square by R square. Yes, sir.
like this. And if I write K cube by 2R, because that is the formula.
Yes, sir.
Here the common was K cube by 2R. We could have taken 2 inside, it's the same answer, right?
Yes, sir.
So if you take 2R outside, it is same answer. So in fact, this is the reverse derivation. So this is the right answer because this is the proving the answer is right because in the reverse process we got the right answer. So this is the right. So our derivation was correct. Okay.
Okay, sir.
Okay. Okay.
Yes, sir.
Now electric field and potential are having a relation, so you can always plot a graph also. So let's say if I give you a graph of a potential versus x as maybe a straight line, and then it forms a parabola, a quadratic equation. So this is quadratic. It's given. So how the graph of electric field will look like if I plot it below it? Let me make it a bit different here. Maybe like this. So like this, I make it like this. Yes. So if you try to plot the graph, how it look like?
So it will be constant for like till the quadratic is till the
Yeah, so
quadratic parabola is reached.
yeah, constant till here, right?
Yes, sir.
And the constant will be below or above.
So below, sir.
Very good. Now it's a quadratic and it's a upward parabola. So upward parabola we can write as something like a x square minus bx plus c, right? Something like this.
Yes, sir. A should be greater than 0.
Yeah, a is positive and b is also positive, hopefully, right? But not necessarily. A is positive. That's it. So if a is positive, just like, if a is positive, then and of course b square is more than 4ac. So we should get the two real roots, right? That's why the coefficient is positive and the b square is bigger than 4ac. So it's a real and distinct roots, correct?
Yes, sir.
So if you differentiate any function like this, you get 2ax plus b. which is the equation of straight line. And
Yes,
because
sir.
A is positive, you can say this must be having a positive
Positive
slope.
slope. Yes, sir.
So after this, you will get a straight line with positive slope. And actually, you will get from here to here till here.
Yes, sir. And then a zero line.
Yeah. It will remain straight line till here. And then it will suddenly become zero. So
Yes, sir.
you will be asked to plot a graph like this in a variety of questions. So okay.
Okay, sir. Sir,
Hmm.
uh, the potential versus x, that was a part of the previous question, sir, or
No, no, just a random question.
okay, sir.
This is the like graphical problem. Okay.
Yes, sir.
So now, so we have done with the ring and the surface and the center, right? So what about the potential due to ring on its axis? If we choose a point P at a distance x from the axis,
So by using the electric field and potential relation,
no,
difference in
we
potential.
can do it directly.
Oh,
You can do it directly. That's easy. You can take in every elementary. So what is the distance of elementary of the ring from the point P?
yes, sir.
So what we should write here? To tell the answer directly.
Uh, yes, sir.
So no matter which point you choose, no matter which point you choose, every point will have the same distance from the P point, right?
Yes, sir.
So here x square plus r square is a constant value, so we can take it out. And a simple integration of dq will give you q only. Understand?
Yes, sir.
So the potential at point P will be,
KQ by under root x square plus r square.
so here the charge distribution matters, yes or no?
Yes, sir.
Matters.
Oh, no, sir. For like anywhere the charge can be like distributed because the distance is constant.
So because every point on the ring is having same distance, so the distribution will not matter. Whenever the distance is same. Okay.
Yes, sir.
So again we cannot here even in this case charge distribution will not matter. Okay.
Okay, sir.
But if we go for the next question, which is like a disk.
So for a disk, the distance, I mean, if we find it on the axis, then the distance won't be constant.
Yeah,
It will be constant only for a particular elementary ring that we take.
exactly. If we have a disk, and we know, but when I don't say anything, it's a non-conducting disk. The conductor should be mentioned, then only is considered. So by default, everything we take as insulator.
So as an immovable charge is everywhere.
Yeah, yeah. So the charge cannot move. That is the underlying assumption without any statement. And if I mention conductor, it means then
On the surface.
so here the disk is there, and the sigma is the surface charge density. We have discussed about this in detail already. So we are supposed to find the electric field at a point P. Now here it is important to mention that sigma is infinite. Because as we change the sigma, the answer will change, isn't it?
Yes, sir.
So first you do one thing, you don't solve directly this question, you can solve first for the answer at the center. So what is the potential due to disk at its center? Center means center, yeah, center you can take in this potential, not emission. In case of electrical, it should be the center of the surface, right?
Yes, sir.
So can you find the potential here?
Okay, sir.
So sigma is given to us. I want answer at O first, and once you get the O answer, then we will go to the axis answer.
Okay, sir. Sir, is it like integral of k sigma 2 pi r dr by r?
Exactly, correct.
Okay, sir. So I'm getting sigma by 2 epsilon naught into r.
Yeah, correct. So at the center, the answer is sigma r by 2 epsilon naught, correct?
Yes, sir.
Now do it for the ring, sorry, for the axis, the quantity here.
Okay, sir.
Method is same, just you have to do the integration.
Yes, sir.
So you will make one ring, you know the answer for the ring, then integrate to get the disk. So try this out. Yes.
I'm getting sigma by 2 epsilon naught into under root of x square plus r square minus x.
Excellent. That's the right answer. This is sigma.
Sir, can you just come back in a minute?
Okay. Yeah, sure.
So,
Yeah.
yes. Sir, are you speaking something?
No, no. Hello?
Hello, sir.
You're solving something?
Sir, no, sir. You didn't
Ah,
give me any question.
oh, sorry, sorry. So I thought you're solving something. I just got lost. Okay, sorry. So I started reading something. I was reading for some time.
Oh, okay, sir.
Anyway. So now we have done with the disk and the ring. And the obvious question is, which is the most important part is called the hollow shell. Okay.
Yes, sir.
So what we can also do for the rod also. So let's try to do it for rod. So if you have a rod, a thin rod which is positively charged, and if I choose a point P, a random location, again at addition Z, but now lambda is given as a linear charge density, and the edges, the rod edge is making angle alpha and beta. So the potential is a scalar quantity, so the direction is not a issue. You can simply find the potential of a part and then you can integrate. So can you try to find the answer? V
Yes,
equal
sir.
to, yeah, do this. Oh, I simply lost. You should have said something.
Sir, I thought that you were doing some work, so I was like waiting.
I just keep on reading something. I have so many books around me.
Oh, okay, sir.
If I count the books on the left of my hand, on the right of my hand, it is roughly on the left we have 30 books, on the right 35 books.
Sir, like all stacked one upon another.
Yes, right and left. I'm in between somewhere.
Wow.
Sandwich between the books. Okay, so this is good. Yeah, I keep on searching for the new problems actually every day
Oh,
because I get
okay.
bored with the old problem. That's why.
So,
Yeah.
so I'm getting the potential to be k lambda. 1 second, sir. So I'm getting k lambda integral sec theta d theta. So
So k lambda, like integration, right?
yes, sir.
Yeah, that's the right answer.
Okay, sir. Sir, I don't know how to
No, no problem.
integrate.
No problem. So that's correct answer. The integration part I'll do. So this is a trick in integration. It's just a trick actually. And the trick is we cannot integrate sec theta. So it's a very famous trick. We write as sec theta and we write sec theta plus tan theta as a product and we divide it. Because it will have no effect, right?
Yes, sir.
But by doing this, the numerator becomes the differentiation of denominator. So dz by d theta will be how much?
Sec square theta plus sec theta tan theta.
Sec theta tan theta. Which is exactly the numerator, right?
Yes, sir.
So the numerator we can write as dz plus ln z. So the answer will be ln. So this will be ln. So it will become, and what we do is we take a modulus because log cannot be negative. So we have to put a, so the formula is, in a way this is not required, but just for the sake of calculation. Anyway, we got the potential due to ring disk. So you can also do it for the annular disk by using the principle of superposition.
Yes, sir. Since it's just scalar subtraction.
Yeah, so now this is pretty easy. You just need to subtract. It's not a good color. Irritating, huh? Which color will go with green? Can you guess?
So orange.
Or anything? Yeah, better. So now what we do is we remove a part from the, So what is the potential at point P? Simple question.
So sigma by 2 epsilon naught into under root of x square plus b square minus under root of x square plus e square.
Excellent. That's the right answer. Very good. So the potential at point P, we can simply subtract that answer, and this is the answer we get. So now the most important part is called. Potential due to uniformly charged spherical shell. Okay. So if we have a spherical shell, and if I'm saying it is uniformly charged, so the radius, let's call it R, charges Q. So the electric field lines due to this distribution will be radially outward, right?
Yes, sir.
So clearly we can understand that the field cannot be present inside, right?
Yes, sir.
Okay. This is the first thing we need to just be careful about. The rest we can derive. So now we would like to know the potential at a point P, which is outside. So the definition of potential is you have to bring some charge from infinity to this point.
Yes, sir.
So for any point outside the shell, we know the electric field will be like a point charge only kq bar square.
Yes, sir.
So if the point is at a distance r away from the center of the shell, how much work is required to come here?
Sir, kq by r.
By r, right?
Yes, sir.
The potential at point P will be the work done upon charge brought, right?
Yes, sir. So kq by r.
Yeah, so that's a simple point charge formula. So there is no big thing. So if r is more than r, then the formula is as good as the point charge formula. No need to worry. Now, but if you want to find the potential at a point P or P dash inside, this is the V outside. So what about the inside? We ignore the thickness of the shell, so the thickness is in zero value technically. So now to come back to the point P dash, you have to walk a long distance, maybe like this. So you will take the same charge, you will take the charge from here, you come to surface, will enter here. So now what will be the work done if the distance is r? So it will be the sum of work from infinity to r and this R is less than capital R. Okay,
Yes, sir.
but the work done by external force, you need to work only when there is a field. So the moment you enter
So
the,
till the
yeah,
capital R will calculate, and then after that, since there is,
no field.
yes, sir.
Yeah, exactly. So the this will be same as the work done by external only from infinity to capital R.
So KQ by capital R.
Yeah. So the answer has nothing to do with the small r, because the
Yes, sir.
capital R will decide. So the V inside is simply KQ by capital R. Nothing to do with the. So it has nothing to do with which point you choose within the cavity. So it is like a cavity. So the rule is the entire cavity will have same potential in this case, and the potential will be same as the surface potential. This potential at surface will be how much? AQ by, so we can use this for R also. It's not like equals, you can use for the surface also. So for any point inside, the potential will be same as surface.
Oh, okay, sir.
And this is a very famous shell theorem. Okay.
Yes, sir.
So the simple rule is every shell will contribute field only outside but not inside. And because it's a uniformly charged shell, so the field contribution is outside. So the moment you enter the shell, there is no need to do any work. There is no need to have. There is no opposition which we are facing. So the work done is not present. There is no work done, and therefore you can just get inside without any hindrance. And so the energy change, the work will be only to surface, nothing beyond that. Okay.
Okay, sir.
So V inside is equals to V surface.
Yes, sir.
But what about the solid sphere? If it is uniformly charged solid sphere, it's a total charge Q and volume charge density rho. And if you want to come, let's say, so for outside point, it's again same. So for any point outside, can we not directly take you where,
Yes, sir.
because the behavior will be same as the point charge.
Yes, sir.
And therefore the potential at surface, again, we can directly write without doing any calculation, KQ by capital R.
Yes, sir.
The only problem starts when you get inside. So let's say if I want to know the potential at a point inside, which is at a distance smaller from the center. So the best way to get the answer is you can just move from surface to, let's call A, to this point P, let's call B. Because we know electric field is like this inside.
Yes, sir.
So which one is at high potential, B or A?
Sir, B is at high potential, sir.
So VB minus ERDR equals to VA from R to capital R.
Yes, sir.
Is this making some sense to you?
Yes, sir.
So the VB is something which we are looking for. So potential at a distance R inside is potential at surface plus integration of ER dr, which is very easy to find, right?
Yes, sir.
Because we know the
Rho r by 3 epsilon naught
excellent.
integration.
So can you substitute and tell me the answer eventually in terms of capital Q? So you derive the way you want, but tell me the answer in capital Q and capital R and small r eventually. What is the final answer?
Okay,
The
sir.
manipulation.
Sir, density is uniform, sir.
Yeah, it's in.
Sir,
Yeah.
so I'm getting kq by 2r into 1 minus r square by r square.
KQ by 2R into 1 minus
R by r whole square, sir.
no, something is wrong. Yeah, I think you missed this three part.
Oh,
Or maybe not. I don't know.
so but then 3 and 3 will get cancelled when we convert
Yeah,
density to q.
right. But still the answer will be different. Can you try once again?
Okay, sir. So it's kq by r plus rho by 3 epsilon naught into r square minus r square by 2 only, right, sir?
And the answer is what is once again? Tell me. KQ by 2R into. Tell me the answer
So
again.
kq by 2r into 1 minus r by r whole square only, sir.
Okay, so okay. So yeah, I think you have missed the limit part. I think the limit you have not taken properly. Upper minus lower.
Yes, sir.
You've taken the limit properly?
Yes, sir. All right. Sir,
No,
I
you
got
have not.
the.
Yeah, you have forgotten the limit actually.
Sir, no, sir. I was like kq by r minus of, that is v surface minus I took, sir.
Yeah.
By mistake.
Okay, so now this V surface is KQ by R, na?
Yes, sir.
And this is rho by 3 epsilon naught R square by 2.
So I'm getting 3 minus r by r whole square, sir.
Yeah, that is I think correct. So So 4 pi epsilon naught becomes k. So we can take common k cube by r.
Yes, sir.
It's a 3 by 2 minus. The better way of writing is k cube by r cube. In fact, 2 r cube into 3 r square. So because the electric field is existing till the center, so you have to keep on working till you reach the center. So potential will be maximum at which point?
So at the center.
Yeah. So the potential will be maximum at the center. And this formula is very, very important from the point of JEE advanced and men's both. So a lot of questions is being asked from this, not only this, but in gravitation as well. A similar formula will be there. The only thing is the charge will be replaced by mass, and the potential sign will become negative because it's attractive, right?
Yes, sir.
So the potential at inside point at a distance r will have value which will not be same everywhere because of the field is present. So at center of a sphere where r is 0, the potential will be maximum. So v at r equals to 0, we can attach how much? K cube by 2r cube minus 0, which is same as okay.
Yes, sir.
And you can look carefully, this is 1.5 times the v surface.
Yes, sir.
So potential at the center is 1.5 times the potential at surface. That is easy to remember. This particular value is very famous. So again, remember this value. Just in case you don't remember the formula, you should know that at center the potential is much. The center potential is 1.5 times the surface potential, which we remember, right?
Yes, sir.
But still, I would say that you should know how to derive and get the answer because it is quite possible that you may have forgotten in examination. So knowing the direction will help you there. Okay.
Okay, sir.
So the next concept, which is very important, is called concentric spheres. Concentric shells. So what if we have a big shell? So potential always follows the principle of superposition. So if I draw multiple shell of different radius, and we'll believe that these are connecting shell. So you can take connecting shell or simply shell. So I need to mention this. So the radius is A, B, and C. So, and the charge on each surface is, let's call it sigma. I'll make it a minus sigma and plus sigma. Or maybe I can make it 1, 2, 3. And then I can put a point O. I can put a point here. I can put a point here. I can put a point here. So we can call the region 1. So we'll just choose some random point. So what will be the potential in the first region at any point R inside? Now we can see that the first point is inside every shell, isn't it?
Yes, sir.
Because the point is within every shell, so the potential will that we have to superimpose is the surface value.
Yes, sir. Sir, is the net charge given, sir, or should we write it in terms of
Sigma.
sigma? Okay, sir.
So the answer will be K Q1 by A, K Q2 by B, and K Q3 by C, and then you have to substitute K value and Q1, Q2, Q3. That's easy for you. So we can
Sir,
add K as
for the Q2Y positive, sir, we are
no,
like pulling.
you have to substitute the value of charge as negative value. That's your
Okay.
job. Okay.
Yes, sir.
So Q1 is what? Sigma 1 into 4 pi A square.
Yes, sir.
Q2 is minus sigma 2 into 4 pi B square. And Q3 is sigma 3 into 4 pi C square. Isn't it?
Yes, sir.
And you can also write K as 1 by 4 pi epsilon naught. So you'll get something nice answer. So can you tell me what answer you're getting at one first point?
So,
Yeah.
sir, I'm getting 1 by epsilon naught into sigma 1A minus sigma 2B plus sigma 3C.
So let me write it down here. So the V1, okay, anyway, it has nothing to do with the R, but it's still, tell me again, sigma 1.
So, sigma 1A minus sigma 2B plus sigma 3C divided by epsilon naught.
Excellent. So if I do it for the second reason, then the second is inside the outer two shell, like B and C.
So, we find the V surface for B and
Yeah.
C and then the exact, like,
Yeah, point charge formula.
yes, sir.
Yeah, excellent. So just do it for one, then I will not tell you to do the again. Just do it for one, then we can leave. We can go to the next answer.
Okay. Sir, once again, can you show the radius? Which one is the smallest sum?
A.
A is the smallest. Okay. Sir. So
Yeah.
I'm getting 1 by epsilon naught into sigma 3b minus sigma 2c plus sigma 1 a square by r.
Sigma 3b plus
So sigma 3c minus sigma 2b
sigma 3c minus sigma 2b.
plus sigma 1 a square by r.
All right. Yeah. That, I think this is the correct answer. Okay. So you know how to write for the rest, right? You can do it for the second, third, and all.
Yes, sir.
So in case of conductor, we have to be a bit careful about induction process, which we haven't discussed, but induction process will not affect the answer here until you do the grounding. So to understand the concept, I'll just go to concentric shell. And the shell thickness we have to ignore so that the radius we can take same for inner and outer one. So let's say we have just two shell, one with radius A, another with radius B. A and B. And we give some charge, let's call Q1, and we give some charge, let's call Q2. So the Q1, Q2 are called the given charge. So you give on a surface. Now, when you give charge on conducting shell, we know that they will create the charge will create an electric field on around itself, and the field will be in the radially outward direction, right?
Yes, sir.
So the field will be like, but we know that field cannot, penetrate the conductor. Field has to stop, isn't it?
Yes, sir.
So from the property of electric field lines, we know that electric field lines do not exist in the bulk of conductor. So it has to stop somewhere below before, right? And then there is a discontinuity, and then a new field will create from after the surface again due to charge on the outer side.
Yes, sir.
So every conductor creates a discontinuous field. So if conductor is present, then we cannot think of continuous field. There is a discontinuity always. So that the
Sir,
whole idea is
discontinuous meaning?
like there is a break of field, no?
Yes, sir, but why only for conductors?
Because the electric field cannot cut through the conductor. No?
Oh, yes, sir.
It cannot go like this. It has to stop, then restart. So however thin the shell may be, there will be a discontinuity of field lines. Do you realize this?
Yes, sir.
With thickness of the shell, you can see it more, you can say, obvious way. So if I make the thickness big, the discontinuity will be for quite a good distance. And if the thickness is negligible, then there will be discontinuity, but you won't be able to see it. Understood?
Yes, sir.
So, for example, if I say that if we have a shell which is like this. So, in this case, if I call the thickness as T, and if I have a point charge as a center, and if I say this is conductor, then electric field will start from the center will stop.
It
Then it
will
will,
terminate at the shell.
yeah,
Oh,
it will terminate and re-grow actually. Why?
so because of the like the charges which are at the surface of the conductor,
So
like
first
the
of all,
negative charge will get induced towards the.
yeah. So the inner surface as a whole, not at one point, the net charge induced on the inner surface will be equals to minus Q,
Yes, sir.
because we need to create a charge which can stop every field lines. So the inner surface will induce a charge which we call minus Q. But if the inner surface will have minus Q, the outer will have to have plus Q.
Yes, sir.
Because the net induced charge on anything isolated is zero, because we don't supply any charge. No? So if negative has come inside, then positive must be here, right?
Yes, sir.
And numerically, this positive is same as the negative value, but this positive will start its own field lines separately. So technically, the field lines which you encounter in the outer world is due to this one. So to find the electric field at point P, we just think of a shell of charge capital Q. So inner combination will have no use. Understood?
Yes, sir.
Which is also obvious from the Gauss law. So if you apply the Gauss law, E into 4 pi r square, then the total charge enclosed is Q only, na? Q
Yes, sir.
minus Q plus Q. So everything if you add will become Q only. So the answer is just like a point charge, and R is the distance from the center. So what I'm saying is that the electric field in the gap, there is a zero field here. And thickness I have drawn to just demonstrate that up to this thickness you won't get any field. Understood?
Yes, sir.
So the field will start again after that. So if I ask you that if we have a charge without shell, point charge at the center, and imagine there is no shell. So let's say think this way. We'll come to that. That's a different question. Okay, no, I'll not. So now what I'm saying is that every conductor will terminate the electric field lines and will recreate. So plus Q1 given to the inner shell will induce minus Q1. But as a result, it will also create plus Q1 on the outer surface.
Yes, sir.
So
So Q2 and Q1 will be like.
yeah, the creator of the outer field. So this electric field, if you again apply the Gauss law, will be the total charge, and you can see the total charge is how much?
Q2 plus Q1.
So the field, of course, the charge contribution will be both, but this entire charge is present on the outer shell. It appears like, right?
Yes, sir.
So this entire thing sorry, is a part of the outer shell. So outer shell will have more charge density than given. So you might have given Q2, but the total charge that you will encounter is Q2 plus Q1 on the outer shell. But the inner surface of outer shell also will have minus Q1. So the net contribution of plus Q1 and minus Q1 in terms of potential will cancel out everywhere, right?
Yes, sir.
So that is why while calculating the potential, I simply did not consider the induction process. Okay.
Okay, sir.
But there are situations in which even to calculate potential, one has to consider the induction process, and those situations are very few. In fact, just one situation, and that's called the grounding, like when you connect with Earth. Okay.
Okay, sir.
So we will study about something called concept of grounding. So grounding basically means connecting a path between the given body with the earth. So you make a connecting path between a body and the earth. So we say the body is said to be grounded. Grounding is also called earthing or earthing, whatever you say.
Yes, sir.
So again, if I have a shell, and let's say we have two concentric shell. So this is the symbolic or diagram for the ground, which means it is connected to the earth. And there are some assumptions about earth in electrostatics. So we say,
So it's too thick.
yeah. So, sorry. So we say this is okay.
Yes, sir.
Sometimes it irritates, isn't it?
Sir, it's not clearly visible while writing.
Yeah. So we say that earth is infinite charge reservoir that is no amount of charge given or taken from earth. So no amount of charge given or taken from earth will affect its potential. For all mathematical purpose, for all mathematical purpose, potential of earth is taken as zero. So anything which you connect with earth will also acquire the potential of earth.
Yes, sir.
Anything connected to earth will acquire potential of earth. That is, the potential will be zero. Okay, that's it. Now, because conductor is having zero electric field inside, so potential of one point of conductor, if you know, then you know the potential of every point of conductor because it is going to be same. So the property of conductor is it is equipotential volume. So what is the property of conductor? I think I should do this separately. So if you have any random conductor, and if you give some charge to this conductor, any random charge, we know the electric field will be 0,
Yes, sir.
and because the delta V we define in terms of if the field is 0, then delta V will be 0, so potential will be same everywhere, right?
Yes, sir.
So the potential of the entire volume will be constant. So volume of conductor is
Sir, can you just come back in a minute?
yeah.
So,
Yeah.
yes, sir. Sir, can you just come back in 5 minutes? I'll have my lunch, breakfast and come, sir.
So what I'll say is, okay, we can end the lecture now because we have already taken 2.5 hours, and then we can start sometime next tomorrow.
Sir,
Or yes,
as in restarting the lecture after 10 minutes, sir?
okay. You when see, I mean, I'm actually almost about to done only. So I was about to end the lecture
Oh,
only. So we will do in the next lecture. Actually, this is what I'm saying.
okay, sir.
Okay. So maybe tomorrow.
Yes, sir. So tomorrow it's a regular lecture, sir.
Yeah, right. All right, all right. Yes.
Okay, sir. Bye,
Yeah.
sir. Thank you,
Bye.
sir.